So, we are talking about mixing in ladles, and I have written correlations for mixing time in terms of operating variables as and I said that this correlation is valid for central injection, that is the next symmetric injection, in a gas starved ladle for certain range of gas flow rate, for certain range of vessel aspect ratio. This constant, which is empirically fitted, this depends on degree of mixing. For example, if I say that it is 99% mixing, in that case obviously this constant is not going to be the same. It is going to assume a much larger value. It also depends on how many porous plugs or how many nozzles or plug. It also depends on the location of the plug. Actually, when we have, for example, a ladle with two different porous plugs, the correlation here for mixing, a similar correlation assumes a value which is very similar to the one that is shown in the above. So, let me explore a little bit about the mixing time. So, suppose when you add a species into the system and monitor a concentration. So, we have concentration versus time at the monitoring location, which could be here, which could be here, which could be here, anywhere in the system. Now, basically we talk about a reactor mixing time, which is important to us, because if mixing time depends on position, since at various locations the intensity of fluid flow and turbulence are not identical. So, the rate of mixing will vary from one location to another location in the system. But what we are interested from engineering sense is that we want a bulk or a reactor mixing time, and that typically is characterized by the mixing of the slowest moving region, because by the time the slowest mixing region is mixed up to a degree of 95%, we can say rest of the system is going to be perfectly homogeneous. So, we have to identify that which is the slowest mixing region in the system, and accordingly ascribe this mixing time with reference to the slowest mixing region, and thereby say that that mixing time corresponds or represents the bulk mixing time or the reactor mixing time itself. Now, basically when a tracer is added or an element is added into the ladle, it cannot go out of the system. At large amount of time, I will have a homogeneous concentration, and that concentration may be this level of concentration which I say as Cb. Now, for example, if I have 1 ton of liquid here, and if I have added 1 kg, the uniform concentration is going to be 1 by 1000 multiplied by 100 in terms of percentage, and therefore, that is the uniform bulk concentration that I have represented, which is nothing but the mass fraction of the added element, the mass of the added element divided by the total mass of the fluid in the system. That is what we are talking about, and that is the final attainable concentration in the system. Now, following the additions, dispersion at, for example, if I have added at certain point of time and there was no concentration of the species in the system, in that case, for example, say I add ferroniobium into steel, and then I find that initially the steel has 0 ferroniobium concentration, so the concentration is 0. So, and if I am monitoring at this particular point, I would say that for some time the concentration will be 0, and then ultimately the concentration will build up and then eventually asymptotically approach the bulk concentration line. So, C versus the concentration of niobium versus time, and then we can say that, well, if I draw a band which is plus minus 5%, so this is minus 5% and this is plus 5% of Cb, in that case I can say that, well, this this is the time that corresponds to 95% mixing grade, and that this point where I am monitoring, if it corresponds to the characteristics of the slowest mixing region, in that case I can say that this mixing time indeed is equal to tau mixing 95% bulk, and this fitted constant here that I have shown is actually corresponding to bulk mixing time in a central gas injection, where I have only one single porous plug and I have the porous plug located at the geometrical central line of the system itself. And for dual porous plug, as I have shown here, the correlation is substantially different, although the exponents on Q, L and R are similar, at least in terms of their nature, because these are negative exponents on R, it is positive exponents, which essentially is consistent with the theory of fluid flow in ladles. Let us now look at the ladle furnace operation, LF, which is ladle furnace. Write it like this. I have mentioned that, or we know that the objective of ladle metallurgy steel making is to adjust the composition of steel, adjust its temperature and improve its cleanliness. We would be now talking about addition of alloying elements. Now, as we process molten steel for vacuum degassing or degassing operations, or inclusion float out or injection metallurgy, and even in holding period, as I have mentioned, that 0.5 degree centigrade per minute of temperature drop. So, there is going to be considerable amount of temperature drop in molten steel contained in ladles, as a result of which we have to compensate for heating. It is not desirable that steel from primary steel making vessel should be tapped at a very high temperature to compensate for this temperature loss or the requirements of the secondary steel making. That is a very stupid way of doing things, because higher is the temperature in the primary steel making furnace, lower is going to be the life of the refractories there. So, it is not desirable to increase the temperature of molten steel beyond a certain level in the oxygen steel making furnace, otherwise it is going to impair the efficiency of steel making. So, having tapped the steel at the requisite temperature from the BOF, we have to have, for the entire duration of secondary steel making, to sustain the entire duration of secondary steel making, we have to have at certain stage heating arrangements, and that is facilitated by ladle furnace. We may be adding, for example, so first I would say that there is temperature drop, temperature drop because of heat loss through the furnace ladle walls from all sides and the free surfaces. The heat is lost, and as a result of which temperature drops. We may be adding some alloying additions to adjust the composition of steel. Suppose we may be adding some ferroniobium, some ferrotitanium, okay, to adjust the composition, and these are solid additions. Their temperature has to be taken to 1600 degree, and they have to melt or dissolve. So, heat of melting we have to supply. Melting is an endothermic process, so we have to supply the heat. Number 3, once the alloying addition melts, it is going to dissolve into molten steel, and then I can say this heat effect of dissolution. This, of course, sometimes this could be positive, sometimes it could be negative, because some heat of dissolution will be exothermic in nature, some heat of dissolution will be endothermic in nature. This is always a requirement. This is always a requirement. This can be a requirement, may not be a requirement. Similarly, we have temperature drop, heat of melting, heat of dissolution, and finally, we can say that heat effect of chemical. The alloying addition may dissolve, okay, it may react with oxygen, for example, or any other elements present, and then some amount of heat may be evolved or absorbed depending on whether it is an exothermic reaction or endothermic reaction. So, there are a lot of heat demand for the secondary steel making processes, and therefore, we have to have some arrangements for heating the ladle. Now, how does a ladle furnace looks like? This ladle is converted into a ladle furnace just merely by, we have basically a roof through which we have an arrangement like electrodes. So these are my 3 electrodes, and we have a roof here, and this would be. So this roof, maybe the entire thing can be attached to an assembly, okay, and it goes like this. So the roof is in this particular arm, the roof can be rotated. So the roof remains with the electrode, remains like this normally, and if you go to a secondary steel making plant, you can see this arm, you can see the roof, and you can see the electrodes hanging in open. Then the ladle is brought after tapping to the ladle furnace station, and then the arm rotates and puts the electrode as well as the cover over the ladle. So if this is the configuration, then I can see that, well, when I have a ladle inside, in that case what happened is the ladle goes something like this. So this is my floor, and then we have a porous plug here through which gases are going to be evolved, and then this is the slag layer, this is the slag layer, and then we have the metal layer here. This is the steel. This is electrode. This is the roof, and roof and the electrode are the movable structures, and now you can see that this can be converted into what is known as a heating arrangement. Through the electrodes, arc can be established under high voltage, and we can have heating, and heat can be supplied to the molten steel. So this is the argon injection here. I can show it with a colored chalk. So this is the argon injection line. So still we have argon injection here. So the bubbles rise here. So there is going to be some amount of convection current, and this convection is going to take the heat which is supplied by the electrode itself. What are these? These are the arrangements for introduction of say alloying additions, and other arrangements for auxiliary additions into the system, and these are our electrodes which are connected to the 3-phase circuits to a maybe 33 kV line, and so on. Now when you supply this, convert the ladle into a ladle furnace, heat is being supplied. In that case, the heating rate is something like, for some rating, typical rating, about 4 to 6 degrees centigrade per minute. How much of a duration we are talking about? We are talking about a ladle treatment to the range of 15 to 25 minutes. During this region, we may have aluminum wire feeding if we have not carried out deoxidation earlier. We can have synthetic slag. One point which I have missed here is also that we may be forming some slags by addition of synthetic slags, because we have, if you have brought it immediately from the basic oxygen furnace, then there is no slag available here. So we have to add some lime also, some spar also, and form a fresh slag. So the formation of a new slag may also, if it is involved, will consume some amount of heat. So basically the supply from transformer, I will quote some data to give you an idea, for a say an 185 ton size ladle, and the supply from transformer is of the order of 33 megawatt, and this is from transformer, and to the furnace the power is roughly about 2 furnace. The power is fed at the rate of 17 megawatt, and this gives rise to a heating of at the rate of 4 to 6 degrees centigrade per minute, and the entire processing is done for 25 minutes, where we may have aluminum wire injection into the system for deoxidation. We may be adding some amount of alloying additions to melt and adjust the composition of the alloying additions of bulk steel, and so on. Okay. Now it will be clear to you that why do you want always the porous plug to be located at the center. Before I go into that, I would say a typical arcing flow rate could be something like normal meter cube per hour to about 80 nm cube. That is the flow rate which is done in arcing. But the objective is to compensate for temperature drop and at the same time expedite melting rates and heat of chemical supply heat of chemical reactions and so on. Now, if you look at the top, look from the top, then it will look like this is the ladle, for example, the top view of the ladle. So, it is a refractory line vessel, so I can draw a thick layer around it. That is the top view of the ladle, and you are going to see now 3 electrodes in this particular way. These are our 3 electrodes. So, this diameter at the center, so they can be encased in a circular cross section, and this is called the pitch circle diameter. Pitch circle diameter, or if you go visit shop floor, you will say people frequently talk about what is known as the PCD. Now, when you are injecting gas, if you inject the gas, for example, if I inject it at the center of the vessel, then this is going to come, the plume is going to surface through this particular region, the plume will be totally surfacing and striking the electrodes directly. On the other hand, if the plume porous plug is located a little bit away towards the wall itself, in that case I can see that the area in which the plume is going to be surfacing will be represented by this hashed area. So, therefore, by displacing the porous plug towards the wall, it is possible to prevent direct contact of the surfacing plume with the electrode. Now, why it is so important? Because we know that in the plume region you have a high velocity. This bath does not contain carbon, the electrodes are made of graphite. So, what happens is this graphite will tend to dissolve very fast, and this phenomena is known in the industry or ladle furnace as what is called as an electrode hunting phenomena. Electrodes get hunted. So, therefore, by displacing the porous plug towards the wall, we are able to minimize the hunting of the electrode or dissolution of the graphite electrodes into the melt. Of course, we must understand that when you displace the plug towards the wall, although we can save the electrodes from direct interaction with the surfacing porous plug or surfacing argon liquid steel plume, this surfacing plume becomes very close to the refractory line wall. So, therefore, you will see predominant refractory wear in the vicinity where I have predominant refractory. So, this is the region where you are going to experience, we are going to see that there is going to be considerable amount of refractory wear. Where it is so? Because the bubbles are rising here, the high velocity regions are located here. So, it is a very high downward velocity which comes close to the wall, okay, and as a result of which, because of this high downward velocity which is shown by a red arrow here, the hydrodynamic erosion of the refractory bricks are very significant. So, typical location, therefore, the location of the porous plug basically is at the mid bath radius position. So, the plug is displaced, plug location in industry, is not at r is equal to 0, okay, but it is at basically r is equal to mid bath radius position. So, we will always do that. I think having said this much, let us now go to the other section of ladle metallurgy. The next important topic for us is degassing. So, the drop in temperature in tapping, because of holding, the drop in temperature because of melting and dissolution processes are going to be compensated through ladle furnace, through treatment in ladle furnace. So, when you get the material out of ladle furnace, it has little bit more temperature than is desired at the casting station. Its composition is correct in terms of solutes, but it may still contain nitrogen which may have been absorbed during tapping of the furnace itself, hydrogen which may have been absorbed because of some wet material, like for example, the lime that I have added or we have added to make the slag. The lime may be hygroscopic in nature, being hygroscopic in nature can contain lot of moisture. So, carbon, silicon, manganese or sulfur, phosphorus and other alloying additions, niobium, titanium, etc. may be right, but at this particular stage the material may still contain some dissolved gases. And once we eliminate dissolved gases, that means the composition of the steel in the ladle is going to be perfect, its temperature is going to be nearly right, okay. And at the same time we have to now only ensure towards the later part of ladle treatment is that what is the level of cleanliness in the melt, and once that point we have been able to address, we can go forward and cast the steel through a steel making tundish ladle mold assembly. So, having fulfilled the objective of the material in through ladle furnace treatments, so the next objective would be that if we want very sophisticated grade of steel, Arctic pipeline grade steel, rail steel for example, which has very little tolerance for high nitrogen and hydrogen. Hydrogen and nitrogen, we all know that hydrogen causes embrittleness, nitrogen impairs toughness of steel very drastically, and also if you are talking of making a deep drawing steel, in that case the significant amount of nitrogen is not tolerated. So, at this particular stage, even beyond ladle metallurgy, we have beyond ladle furnace, we may have some nitrogen and hydrogen, and which we have to be eliminated. And the technique that are used are the commonly called the degassing techniques, and these are basically the vacuum degassing technique. Degassing will be facilitated under vacuum, and once I tell you the principle briefly, you will understand that why vacuum facilitates dissolution. For example, if you take nitrogen, which is dissolved in steel with an underscore, and then if you consider the equilibrium of this reaction, and this nitrogen, it is driven out of the melt and it goes into the gas phase as. Similarly, if you have hydrogen in the melt, and then we have the equilibrium of this reaction is half of H2. Similarly, under vacuum, the carbon oxygen reaction can also shift. We have studied in primary steel making reaction C plus O is equal to CO at 1 atmospheric pressure, and that curve that is drawn for percentage C against percentage O, that line will shift depending on what the pressure is. So, whatever carbon and oxygen are there in the melt, under the application of vacuum, the curve is going to be shifted. So, the equilibrium, CO equilibrium will also shift under vacuum. It is at once clear that smaller is the partial pressure of nitrogen in the gas phase, more will be the tendency of this reaction to go from the left to the right. This is the simple principle of solubility product. On contrary, we can say that higher is the concentration of nitrogen in the product phase. This is the product, this is the reactant. So, higher is the concentration of nitrogen, more will be the tendency or to go in this direction, or less will be the tendency. So, by continuously removing nitrogen from the system, we will be able to facilitate this reaction to move in the forward direction. By continuously removing hydrogen from the system, we will be able to facilitate metal to lose hydrogen, and same is true also with carbon monoxide. So, therefore, all these gas forming reactions, as I have enumerated here, the 3 reactions, they are going to have a greater tendency to move in the forward directions from left to right under the application of reduced pressure, and that is why we carry out the degassing operation in steel making under reduced pressure. And what sort of a pressure we are talking about? We are talking about 1 millibar pressure. It is an extremely low pressure, and at that pressure we are going to hold the steel for some amount of time, and of course to obtain that kind of a pressure, we have to have pressure tight chambers as well. And there are various kinds of degassing processes which are there in industry. Now, typically 3 different types of processes are known. One is called stream degassing, which of course has become obsolete, stream degassing. The second one is called tank degassing, and the third one is called circulation degassing. So, I say that this is not there, but it is good to know a little bit about stream degassing. What does that mean? That means that we have a chamber, a ladle. So, this is a small little ladle which is sitting here, which contains molten metal, and then we have molten metal falling in another ladle which is contained in a big chamber. So, this is ladle 1, this is ladle 2, and this is the vacuum chamber. And this is the suction. So, when the metal falls from here to this place, what happens is the stream is not coherent. You have seen that if you open a tap, the water stream from the tap is highly non-coherent. It does not fall like a cylindrical shaped one. So, there are droplets. So, there is a large formation of droplets because of the application of high pressure as the material falls there. Large surface areas are created, and large surface area essentially implies, because these reactions are occurring at phase boundary. You must realize that this is in the metal, this is in the gas phase. So, this chemical reaction must be occurring at the phase boundary. These are heterogeneous chemical reactions. So, therefore, the rate of the chemical reactions are going to be related to the surface area. So, as a result of exposure of the stream to vacuum in the form of tiny droplets or high length, what we are basically doing is we are enhancing the surface area through which this sort of reactions, which of course there is low pressure system here. So, we have increased the area and we have a low pressure system. So, as a result of which lot of hydrogen and nitrogen from the metal will go to the gas phase and they will be ultimately drawn out. It is not a very efficient process, and that is why it has become very we cannot reach very extremely low hydrogen and nitrogen through these techniques, and that is why it has become obsolete. Tank degassing, on the other hand, is an improved version of this. Tank degassing is basically adapted for small ladles. Small ladle means how much? We are talking about 50-ton ladle, 60-ton ladle, 70-ton ladle of that particular size. Circulation degassing is most popular, and this is for most popular, and this is for large capacity ladle, large capacity ladle. But principle everywhere is same: increase surface area, increase subject to low pressure system, and that is how you are going to eliminate the gas phase itself. The efficiency of circulation degassing is the highest, and that is why it has become more popular, and it is widely accepted for larger capacity ladles, because the capital investment in circulation degassing is very heavy. Circulation degassing again has two different types. One is RH and one is DH, and this DH circulation degassing has become virtually obsolete today. It is RH degassing process, which is universally some versions of RH degassing of course is available, but the essence of this I am going to describe, and the RH degassing is being applied in most of the large capacity steel plants on a routine basis. So, coming to tank degassing essentially means that we have a tank, and in this tank we have a ladle, and this is the ladle which contains molten metal, and there is argon injection here. This is argon injection, and the entire thing here is subjected to, we may have some windows also through which one can see through that what is the state, and then we have suction here, argon is injected here, we have slag here, and the plume is generated, and this produces low pressure system, and as a result of which fresh materials are going to be exposed to the low pressure, and there this particular reaction is going to facilitate. We must understand that without argon, what is the scenario that we are going to have? We are going to have molten metal covered with it completely by slag. So we want to bring molten metal in contact with the vacuum or the atmosphere, and as a result of which what happened is we have to blow in argon. Also we must understand that the hydrogen or nitrogen which is sitting here, okay, has to move to the free surface, and then only the interfacial chemical reactions can take place at the gas or ambient metal interface. So therefore we understand that the injection of gases during vacuum, argon gas during vacuum degassing process is extremely important, as it facilitates to bring in fresh material towards the slag metal interface or towards the metal ambient interface, and as a result of which fresh metals containing hydrogen and nitrogen are exposed to vacuum, and where this particular chemical reactions take place, producing ultra low nitrogen and hydrogen steel. Now there we can have initially what is known as a suction period. So basically we have this tank which is there in the degassing area. So within this tank, this particular ladle which contains the metal is lifted with an overhead crane, and then it is brought and kept inside the tank. So that is the arrangement, and then an additional cover is brought, and that cover is put over the tank, and this is this particular cover I am talking about. So once this cover is brought, it is made airtight, and then the suction starts, and one can monitor through this particular window, which I say is a see-through window. This is the one, okay, and see the progress of the dissolution, progress of the degassing process itself. So the tank is an enormous structure. It could be, if the diameter of the ladle is 3 meters, this tank could be about 9 meters to 10 meters in diameter. So huge tanks are available, and these tanks are made of extremely thick steel plates. Suction period typically could be, it depends on the size of the ladle. Basically I am talking with respect to a 50-ton ladle, where the suction period is 15 minutes, and holding period means depressurizing period, holding period is about 15 minutes, about 30 minutes of processing time for about 50 tons of steel. And during the suction period, the pressure here in the chamber continuously drops, and then once 1 millibar pressure is reached, at that particular time you give about 15 minutes of holding, and during this particular duration with argon gas injection, these reactions are driven towards the forward direction, and as a result of which we produce low nitrogen and low hydrogen steel. Now in degassing process there could be significant drop in temperature also. So therefore the material that is brought here actually is overheated to some extent in order to compensate for the degassing process, because LF is before degassing process. So to compensate for the temperature which is going to be lost during the degassing process, and what we are going to see, we are going to notice that there is a temperature drop because of the degassing, and this temperature drop has to be compensated by the ladle metal, by the LF station. So therefore the material which comes from the LF is at a higher temperature than is required by the continuous casting bay in order to compensate for the temperature drop in the vacuum process itself. We must understand here that because the pressure is extremely low, okay, the bubbles are subjected to just the ferrostatic head, so the bubbles really grow enormously in the system. So, as a result of which the same gas injection which will produce say x amount of stirring in this system under vacuum, it is going to produce significantly higher amount of stirring because of the increase in the gas volume, because as pressure goes down the volume of the gas increases. So, the volume of the gas for the same gas flow rate is going to be higher here than it is here. The size of the bubbles are going to be higher here than it is here, and as a result of which even a small little flow rate is going to cause considerable amount of stirring in the system itself. This stirring produces the slag eye area and breaks the slag. This is the slag, this is the slag, and this is where the metal directly comes in contact with the atmosphere environment. It is not here, there is no contact with the metal and the atmosphere here because it is covered with slag. There is no contact here, it is only through this surface that the metal comes in contact with the ambient atmosphere. Now, we have a circulation time concept, and that circulation time basically is 3 times the mixing time. So, I can find out that what is the mixing time of the ladle. Okay. Suppose if I have a correlation like the one I have shown, mixing time is equal to 25.4 into q raised to the power 1 by 3, etc., etc. So, if I know the mixing time, so I can substitute the parameters, the gas flow rate, the depth of the liquid, the radius of the vessel, I can calculate the mixing time, and then 3 times the mixing time will roughly give me what is known as a circulation time, and that means that one time to circulate the steel in the system we can have, which could be about 3 times longer than the mixing time, and we may need 9 or 8 circulation or 13 or 14 circulation depending on the level of final attainable hydrogen and nitrogen, and accordingly we can, knowing the mixing time, we should be able to find out that what is the processing time. The number of circulation actually necessary could depend on the size of the ladle, and just for the sake of getting an idea that for a 100-ton ladle size about 13 to 16 circulation may be necessary, and each circulation time corresponds to about 3 times of the mixing duration. So, that gives you an idea, and this is needed to get a hydrogen approximately about say approximately 1 ppm hydrogen. In order to attain dissolved hydrogen in the system, you require about 13 to 16 circulation. So, this will depend basically on the size of the ladle, how many circulations are necessary, and the final composition of the desired state. Now, the last and the most important type of degassing is the RH degassing process, and this is a this is called a circulation degassing. The generic name of the process is circulation degassing, and it will be clear to you in 1 minute that what do we mean by. Now, the ladle is here, the porous plug through which argon is injected is here, and then we have basically and then we have argon again here. So, this argon may be because of stirring, and we have argon which is being injected through. This is the apparatus actually, the circulation RH degasser, and this degasser is brought and it is going to be immersed into molten steel. It has 2 legs, as you can see. This is called the left leg, and this is the right leg. So, when you immerse this degasser into molten steel and then introduce a lift gas argon here, so the argon gas, because of its buoyancy, is going to rise up vertically, and as the argon gases is going to rise up, molten metal will also rise along with it. So, I have molten steel, this is the argon bubble here for bulk stirring. This may be there, may not be there. So, it is causing some stirring here in order to take material from here to the left leg, and then because of this lift gases which rises through the left leg, it draws molten metal along with it. Now, as it draws the molten metal, low pressure system is going to be applied here, and as a result of which what happens is the material will flow from here to here. So, the argon gas bubble is going to be introduced here, the bubbles are going to rise, along with it the molten metal also going to rise into the degasser, and then it is here we apply suction. So, the molten material here is all exposed to vacuum, and this is the plate which may be acting as a heater to supply heat to the molten metal, because I said that there is going to be significant amount of temperature drop. So, the bubbles injected here is going to enhance or increase in size because of the application of the vacuum, and as these big bubbles rise with extreme rapidity, they are being drawn by the high pressure at a very fast rate. So, there is going to be lot of molten material drawn into the upward leg, and as the material is drawn into upward leg, from somewhere the material has to come, and as a result of which some circulation is going to, and this argon gas injected through the porous plug, this is now going to bring in more and more fresh material into the leg, and as a result of which a circulation that is established here is going to expose all the material contained in this system under vacuum, and as a result of which the material will be effectively degassed. We can also have certain trim composition adjustment allowing additions, and it is a highly efficient degassing process. So, this is the general convection current, okay, generated because of the porous plug, and this is the plume, and as this plume causes the overall bulk recirculation. On the other hand, this argon, which is I have shown being introduced into the left leg, is termed as the lift gases itself, lift gas, and this lift gas actually draws the material into the vacuum chamber, exposes it to vacuum, and as a result of which we have metal vacuum or metal ambient interaction here. So, we have the heterogeneous chemical reaction or the degassing reactions taking place not here, but it is taking place really here, where the material or the metal is going to be exposed to the ambient medium. But these circulations are also equally important. This lift gas also is important in order to expose fresher and fresher material at every instant of time to vacuum itself. So, these are called the snorkel. This is called a snorkel. This left leg and the right leg and the entire thing, what is being immersed into molten metal is the snorkel, and this snorkel has arrangements for suction, and we can apply the same pressure, maintain 1 millibar pressure or even lower, and then we can make certain alloying addition. The entire chamber is sealed and is operated in such a way that we can monitor temperature also by inserting sensors without breaking the vacuum. All these alloying additions, temperature measurements, etc., can be carried out by breaking vacuum itself. And it is important that the legs are submerged to a certain depth below the slag layer, because we are going to have some slag here. So, they have to go really below the slag layer, such that it is not slag what is drawn inside, it is the molten metal. So, some amount of submergence of the legs inside the metal is very, very important. And as once the molten metal is subjected to the degassing techniques, the nitrogen and hydrogen level in the molten metal can be significantly. So, at the end of inert gas stirring, or if you look at from furnace stepping operation, we have furnace stepping, and then deoxidation operation, then ladle metallurgy operation, and then finally degassing operation. What we have been able to achieve is that we have been able to reduce oxygen content of the melt through degassing. We have to increase temperature of the melt, and through LF operations we have been able to adjust composition correctly in the LF itself. We have been able to remove hydrogen and nitrogen through degassing. So, composition is correct, less amount of hydrogen and nitrogen, temperature is up, oxygen is down. So, whatever was the demerits or the problems associated with the primary steel making, that the material contained lot of oxygen because of oxidation refining reactions. It had the composition was not right, only the carbon content was right, and that during tapping or transfer operations we had a lot of pickup of hydrogen and nitrogen. All these have been regulated or controlled effectively through inert gas stirring, through ladle furnace, through vacuum degassing process. So the final frontier of this is now we may still have some issues regarding inclusions, and also in some specific cases we may be concerned with what is known as desulfurization. And inclusion control and inclusion modification, as well as inclusion control and modification, these come under the jurisdiction of what is known as injection metallurgy, shortly IM. Desulfurization, we all know that blast furnace is the ideal place for removal of sulfur, because blast furnace provides us with a relatively basic slag. It has extremely low oxygen potential or highly reducing environment, and also we have relatively low temperature which are correct, right, for relatively high temperature which are thermodynamically correct for desulfurization. Now, that the slag is not really very basic, and sometimes that we cannot have too high temperature in the blast furnace, because if you may have the too high a temperature, one to make the slag fluid, one to drive the desulfurization reaction from left to right, in that case what we experience is that we have too much of a silicon in the metal, because then silicon reduction reaction will take place at elevated temperature, because there is a lot of coke in blast furnace, and as a result of which the pig iron is going to contain a lot of silicon, and that silicon is going to drastically affect the performance of the oxygen steel making processes, because more silica means more temperature, more silica means more slag volume, more silica means more lime. So therefore, if we cannot eliminate lot of sulfur in blast furnaces, sulfur removal cannot be achieved to a significant extent in basic oxygen steel making furnace, because the conditions thermodynamically are not favorable there. We have a high oxygen potential, and we all know that sulfur removal is not facilitated under oxidizing environment. So therefore, even beyond primary steel making, even beyond LF and vacuum degassing processes, we may have the sulfur content of the steel, depending on what kind of a raw material we use, relatively high, and there we may be required to produce an ultra low sulfur steel. Also, we may have generated a lot of inclusions in the steel. We will talk about inclusions later on in this course, but let me first tell you that inclusions basically are unwanted and foreign materials in steel. What are the sources of inclusions? The sources of inclusions are basically due to entrapment of the deoxidation products or entrapment of the slag in the melt. For example, I may have some slag particle, I have an intense stirring, and that slag particle may be entrapped, and it may never get floated up from the molten steel system. So final steel cast will show that yes, indeed, slag particles have been entrapped at certain stages of steel processing. Similarly, I may have deoxidation products which may not have adequately floated, and these deoxidation products actually they take such a long time to float that they manifest in the final cast steel. So I cut a section of the steel and I find, well, there is a lot of manganese silicate there, and I can immediately say, well, I deoxidized the bath with manganese, silicomanganese, and that's why manganese silicate has come. So the inclusions are basically of deoxidation products in these particular cases. Also, we may have refractory from the wall worn out, and that refractory piece may get also entrapped. So various kinds of foreign materials, and these are inclusions. When we are talking of inclusions, these are non-metallic oxides. That is the basic nature of this. When you do continuous casting, we will see that the mold powder can get entrapped into molten steel, and the mold powder can manifest in the solidified billet or blooms or slabs, and they also form some. They are also called inclusions, but the inclusions, depending on their origin, where from they have come, they can be said that they are either endogenous inclusions or exogenous inclusions. Endogenous inclusions are basically deoxidation products. Entrapped slag, entrapped refractory particles are basically exogenous. No matter what they are, they are not wanted because they impair the mechanical properties of steel. So, it may be necessary in certain cases that, well, since the inclusions are there, they may be solid inclusions, we can inject certain species into the system, and as a result of which we can convert the nature of the inclusion. For example, if you inject calcium into steel, in that case we can form, for example, calcium aluminate. If I have already alumina inclusions, and then I can form calcium aluminate inclusions, and which may have some complex with silica, etc., for actually give rise to a liquid phase inclusions, and which has a greater tendency to come in contact with each other. Liquids have a greater tendency to coagulate or coalesce, and if they can become bigger, they can really rise up to the slag metal interface very easily. So, modifications of inclusions and desulfurizations may be necessary in some processes beyond, and these are basically beyond the ladle metallurgy treatments, conventional ladle furnace vacuum degassing techniques, and there we say that we have a host of techniques, particularly injection metallurgy, where we inject certain materials. And what do we inject really? We can inject powder, and that powder will be injected with a carrier gas. For example, a carrier gas could be argon. I do not want to use nitrogen here, because I have just now subjected the steel to tank degassing process or circulation degassing process, spent so much of money and effort to remove nitrogen. So, the carrier gas here has to be such that it does not contaminate molten steel. So, argon is an obvious choice. And why do we use powder? Again, we are talking about multi-phase reactions, reactions between various phases, heterogeneous reactions, where we are talking about reactions at the phase boundary. So, we know the rate of the heterogeneous reaction is directly proportional to the surface area. So, therefore, the powders, when they are injected into molten steel, they have extremely high reactivity, okay? And this is basically pneumatic injection of powders with a carrier gas. We can do this, or we can have cold wire injection also. Cold wire injection essentially implies that we have a cylindrical wire, okay, and in this we have really powders are encased. That is what it is. So, there is a coating, and within this, so as the coating melts, and as this wire is going to be injected, cold wire is going to be injected into steel, this surface is going to melt, and once this surface melts, these solid particles are going to be released in the system itself, providing large surface area, large reaction rates, and so on. So, if you have sulfur, for example, in steel, in that case the sulfur can be taken care of by injecting of calcium. Calcium sulfide may form, and we can also say that if you have inclusions like alumina, etc., and if you inject calcium, in that case we will be able to control inclusion morphology as well as inclusion shape and characteristics. One important objective or problem with calcium injection is the calcium under steel making condition is gaseous in nature. At 1600 degrees centigrade, calcium can stay as vapor. So, whatever calcium you inject either in the form of powder or in the form of a cold wire, that calcium, when it will come to contact with molten steel, it is going to immediately become vaporized. Now, if calcium becomes vaporized and its vapor pressure at under steel making condition is roughly about 1.81 atmosphere at 1600 degrees centigrade. So, this implies that immediately upon contact with molten steel, calcium is going to be in vapor phase. Now, if it is vapor phase, in that case what happens is the vapors being lighter, they will immediately try to come out from the melt itself, and if they come out from the melt, the contact time between calcium and molten steel is going to be extremely small, and as a result of which you will not be able to dissolve significant part of calcium, because if sulfur is sitting in the melt in the dissolved form, you want calcium to react with this sulfur. The calcium from the coat powder has to get into the state of dissolution. The calcium powder has to melt and dissolve okay, if not if it becomes gas also, it has to dissolve. The calcium powder has to dissolve into steel, get into this stage, and then only it is the sulfur atom which is going to be accessible to it. But this dissolution will depend on how much of contact time is there. If the calcium, injected calcium, does not stay there for a long amount of time and it immediately surfaces in the form of big gas envelopes or bubbles, we can understand that there is virtually going to be little scope for calcium to get dissolved. And indeed, this is a very important issue in calcium injection, that the recovery of calcium is extremely small. And also, even if you can increase the contact time, the solubility of calcium in steel is roughly about 0.05 wet percentage. So as a result of which, under steel making condition, although injection of calcium has many advantages in terms of inclusion, morphology, control and modification, okay, it is going to be highly expensive affair, because the solubility is less. A lot of calcium that we are going to use, we are going to inject into the melt, actually not do any useful work, rather than they are going to go and escape to the surrounding. So this is a very important point, and that's why calcium treated steels are extremely expensive. So we can have, they say it, CASI wire, calcium silicide injection, and calcium fluoride, CAFE wire. Okay, so both the ways they are injected, the powders could be calcium silicide or calcium fluoride, and not in pure form though, and that's the way they are injected to steel. How to carry out desulfurization? So by coming back to this particular issue, before we start desulfurization, I would say that by injecting calcium into molten metal, okay, by either powder with a carrier gas or in the form of a cold wire, just like the way we do aluminum wire injection, which I have demonstrated, it will be able to pump in calcium into molten steel, and whatever calcium is going to dissolve, that calcium is going to react with alumina inclusions, and it can aid in formation of complex inclusion compositions, whereby it can control the shape as well as nature, shape, composition and nature of the inclusion itself. As far as desulfurization is concerned, desulfurization basically is carried out at a relatively high argon flow rate in the ladle. Now we have, for example, we have this ladle and then porous plug here, and then we have a slag layer here, with a slag layer here. So you make fresh slag with lot of calcium, because now you want to desulfurize the bath, and as a result of which, what you require is that a highly basic slag should be there. So you prepare more lime, you add more lime, dissolve more lime, and make a highly basic slag. And desulfurization, as you all know, is a slag metal reaction. So the larger is the contact area between slag and the metal, you are going to have more effective desulfurization. So you can pump in basically more argon, relatively more argon rate. I have told you that 40 normal meter cube of argon per hour will be blown through the porous plug when we are doing arcing. When you are doing rinsing, maybe 5 to 8 normal meter cube per hour, but when we will be carrying out desulfurization, this could be about 200 normal meter cube per hour. That is the flow rate that we are going to be. So this is for desulfurization. Arcing, we are going to say 40 normal meter cube, 40 to 80 normal meter cube per hour, and this is arcing. And rinsing, we are going to say 5 to 10 normal meter cube per hour, and that's the kind of. So significantly higher flow rate is used under to desulfurize the bath. And as you all know that desulfurization is slag metal reaction, so there is going to be the surface area is going to be very, very important. So when you blow gas at a very high rate, what is going to happen? There is going to be extensive amount of slag droplets which will be entrained in the vicinity of the plume, because the surfacing plume will go up, it is going to go down, and there is going to be tremendous amount of circulation, and as a result of which what happened is lot of slag metal emulsion and slag droplets are going to be entrained, and which is drastically increase the flow rate, drastically increase the surface area, and aiding in desulfurization reaction, which is basically a slag metal reaction. And of course, we must understand that when you do this, we have a tremendous fluid dynamic activities in the plume region, because the flow rate is very, very large, and as a result of which we can have lot of droplet formation, lot of reoxidation. So it is perhaps desirable that the entire thing is covered up and carried out. Okay, this operation can also be done in tank degassing operation. For example, desulfurization can be carried out where it is facilitated under vacuum. So there is at least no scope for oxygen absorption or nitrogen absorption from that. So if you do it in an uncovered level, if you use very high flow rate of 200 normal meter cube per hour and have no cover there, in that case lot of nitrogen and oxygen can really get into molten steel, jeopardizing and the quality which we have been trying to meet through ladle metallurgy steel making operation.